Okay, so welcome to the afternoon session. After two wonderful lectures in the morning, you had a tutorial to bond over. And for our final talk of the day, we have Satya Amar. So he did his undergrad, that is B Maths from ISI Bangalore. He's currently a student of M Maths at ISI Bangalore. And why is he here? Because we thought he's closer to your age. So you might have lots of relations, similarities, and love for maths. So having a talk from someone who is closer to your age and have same affinity towards mathematics would be wonderful. And in our high school, we just largely see finite mathematics, like some 35, 57 numbers. So now he's going to talk about beyond finite.
So the main theme of this talk is going to be that a lot of very obvious or basic statements about mathematics fail to hold when we move from finite to infinite. Let me give you an example. Like, are you convinced with the statement that the sum of two real numbers is a real number? So we can extend this result to the sum of three real numbers is a real number. The sum of four real numbers is a real number. But at any point, are we ready enough to say that the sum of infinitely many numbers is even a number? So on that note, let us try to do this problem. Like, yeah. So does anyone have any idea how to solve it? Huh? Okay. What? It's a GP, right? Like, what will be the procedure? Yes. Like, if you want to find its value. Yes? Okay. Okay. Yeah.
Sir, so I was telling we can consider this sum to be some S, sir.
Okay.
And then 2S is nothing but 2 plus 1 plus 1 by 2 plus 1 by 4 and so on.
Yes.
So we are getting 2S is equal to 2 plus S. So S is equal to 2.
Okay. So that also works. Coming to the solution. It is very similar to what you said. Like, I take S to be 1 plus half plus 1 by 4 and so on. And then I multiply this whole equation by half, which gives us the second equation. Now what we see that a lot of terms are common in both the equations. So when we subtract these two equations, we get this result. And therefore our final answer turns out to be 2. Is everyone convinced with this argument? Now let's apply the same idea to the sum of this series. Let's see what happens if we apply the idea to this series. Here we take S to be 1 plus 2 plus 4 plus 8 and so on. Then 2S turns out to be 2 plus 4 plus 8 and so on. Again, we have a lot of common elements, and subtracting them will give S equals to minus 1. But can we accept this solution? Okay, so what is the reason? Can I? Okay, sum of positive numbers can never be negative, right? Okay. What do you mean by divergence? Okay. Even the previous sum keeps on increasing, right?
No, 1 by 4 is lesser than 1 by 2, which keeps reducing the next term.
Okay, so you mean in that sense. Okay, so everyone has the idea that this sum should in some way turn out to be infinite or the series diverges. But what is the problem with this calculation? Why is it giving the wrong answer, like a very absurd answer?
You're multiplying by 2 is wrong because you're dealing with infinites. Multiplying by 2 doesn't have any meaning.
Yeah, that's the point I was trying to make. That's all right. So we can hold our thought on this one, and we turn our attention to this, like adding elements in a matrix. Now I have this matrix. I would like to do two things with it. First, I'll try to find the sum of each row in this matrix. So can you tell what is the sum of this row? Okay, it turns out to be 6. The sum of this row turns out to be 15. Okay, this turns out to be 24. What is the sum? Okay, 45. Now let's try to do the same thing column wise. The sum of the first column, 15. Okay, what is this? Okay, 45. So can you explain why this is happening? Like, yeah, like in any case, what we are ultimately doing is adding up all the elements in this matrix, or a table, you can say. Now let's try to do the same thing on this table. Here I have kind of, you can say, an infinite matrix. Here, what does the sum in each row turn out to be? Like, let's start with the first row. What is the sum in this row? Okay, so 0. Just to be clear, the spaces which I have not filled, they are all 0 elements. The sum of second term, rows, and for any row, what will be its sum? Can you generalize? Okay, so these are all zeros, and adding up the row elements should give. Now let's try to do the same thing with columns. Sum of the first elements in the first column, 1. Sum of elements in the second column, 0. Third column, 0, and so on. What is the sum of the column elements? 1. Now, why is this happening? Like, does anyone have any explanation for this? Okay.
The last term is -1. How do you know?
Like,
We define it because we can't.
okay.
So
Yes?
the last column should come as -1, and so the sum of this will also become 0.
Okay.
And hence overall it becomes 0 again only.
Okay. When are you reaching the last term? Like, what should be the index of that?
Infinite.
Like, can infinite be an index?
Maybe, but we need to consider the case, and it should be 0 only.
Like, why? Like,
Because we are adding all the elements in the table, so anyway the sum should be 0. So in this case, if we don't consider infinite as a index, then it wouldn't match, right?
yeah, it's not matching. Yeah, that's my point.
So in this case, infinite has some significance in the index.
Like, it's not, like, we cannot, like, infinite is not actually a number, it's a concept. To give you an example, so these two equations have a completely different meaning. Here we are assigning x a value, but here what we are trying to say is that you think of any value, x is greater than that value. So x is something which is greater than every real number. So can I say that it does not lie in the real set of real numbers? So if I want my indexes to be a natural number, we are not reaching infinite. That's the point I want to make. So to make things more clear, like you can look at the sum of these elements from the perspective of series. Like, is it convincing that the series is 1 minus 1? Like, we are alternately adding and subtracting 1. So, like, if I put my brackets like these, the sum turns out to be 0. This is what we were exactly doing when we were summing up the elements in each row, right? Now if
Sir. Hello.
yes,
How do you know that the last term is not minus 1? Oh, it is minus 1. How do you know it is minus 1?
what is the last term? Like, are we reaching the last term? That's my point.
It can be either 1 or minus 1.
Yeah. But does it have a last term? Like, that's my point. Like, if for every term you can have a next term, right?
Yeah.
So are we exactly reaching something like a last term or anything like that? This equation goes on, right?
So there's no last term for the first one. In the row sums, there's no last term. So even in the column sum, there should be no last term.
Yeah, that's the point.
Then how can you conclude that S is 0 for the first one?
S is 0 because we are putting brackets like that. We can pair up, they will minus out. They all are individually zeros, right? And we are ultimately adding zeros. How many of them we don't care, like they'll turn out to be 0, right? And the problem is that we shift the brackets by one step, the sum turns out to be 1. So, like, what point I'm trying to say that we are assuming some basic properties of adding numbers, but they are giving anomalous results in the case when we are taking a lot of numbers, like infinitely many of them. So to give an exact explanation of these anomalies will require a lot of terms, like someone said divergence or something like that. But just to give you an idea of what is going on, you should be asking these questions. Like, the first question is S actually a number? So, like, if it's a number, fine, but if it's not a number, then what is the sense of multiplying this by 2? Like, what are we actually multiplying by 2? Or what is the sense of doing any calculation beyond that? And another point I was trying to make is that the rules of commutativity and associativity fail to hold when we are considering adding infinite numbers. Like, everyone is clear what does the commutative law and associative law say, right? Just to make sure, like, the commutative law is this, where A and B are real numbers, while the associative law is this, where A, B, C are real numbers. So we cannot put brackets anywhere according to our will and expect the answer of an infinite term to be same every time. And is that explanation, like, satisfying enough? Okay. So you have something to say? Like, oh, okay. Sorry.
We are pairing into brackets as 1 minus 1. We arrive to a conclusion that sum of these groups is 0.
Okay.
And we say that it is actually ending with -1. So at last 1 minus 1 gives 0. Then down adding to the columns, you say that you change the group of brackets with group the other side. So you get 1 plus -1 plus. You keep a bracket between -1 and +1. So can't we say that adding the columns is groups of odd numbers?
Actually, I think the point you are trying to make that in the first I'm assuming that the last number should be -1, and in the second I'm also assuming that the last number is -1, right?
Yeah.
But will this series, like any infinite set of numbers, does it have a last number? Like last index or anything like that?
It doesn't have, but as you grouped into 1 minus 1, so we can assume as the ending must be as 1 minus 1, the ending number must be -1.
But is there an ending number?
So
Is there an ending number?
it's not there actually, we are just imagining.
Thing is weird. Okay, like the thing is that the list goes on. Like if you find a last number, if you find a -1, this series makes sure that there is a 1 following that and there is a -1 following that. Like the list is continuing.
Yeah, then how can we say that 1 plus bracket of -1 plus 1 and so on gives 1?
Because like even if we remove the first one, we can find a -1 following that and then we can find a 1 following that. We end here. Again we can find a -1 following that and we can find a 1 following that. Can I do that in like infinitely many times?
Yeah, we can do so.
So that's why like
Thank you, sir.
okay, so the point I was trying to make is that when going from finite case to infinite case, we need to like check for all the basic, we need to at least check for most of the basic results if they hold or not. So in that spirit, let's move on to the second part of our lecture. Like here I'll be taking like two statements which look very obvious and like we don't need to prove them, but we'll see that their proofs have very interesting ideas. So moving on, the first statement, you must have probably seen it yesterday, but still I would like you to take some time and try to absorb the patterns in this proof, like how this proof is structured and how one argument follows from another, because it has a very nice, even this statement feels obvious to a lot of us, it has a very nice proof. So if you want, you can read for some time and like okay, so first of all, what kind of a proof is this, if you want to classify it? Okay, so it's a proof by contradiction, and what do we mean by that? Okay, so can I say that proving it by contradiction, I'm actually saying that my statement is right by proving that it cannot be false. Okay, so let's see how the proof goes. Like first I take that my statement is false. Then what does it mean? That we have a finite number of prime numbers. We try to collect all of them, and there's this one tricky number which comes up and shows, hey, you have missed me from my list, or you have missed a prime number from your list. And like no matter whatever collection we take, this tricky numbers can come, like we can apply the same strategy to come up with a number and show that you have missed some number from the list, and that is the contradiction. So we say that the collection of prime numbers cannot be finite. So that was the structure I was talking about. I would like you to keep that structure in mind, because we will have a very similar proof for our next statement, which is that the cardinality of the set of natural numbers is strictly less than the cardinality of the set of real numbers. So does anyone have any explanation like why this is true? Anyone? Yes? Yes? Okay, so like what I understand from your statement is that like natural numbers, real numbers have some extra elements, like it contains all the natural numbers and it has some extra elements also, right? Okay. Okay, what you want to say? Okay, so like you are also kind of making the same point, right? We can get extra numbers other than the natural numbers. Okay, yes ma'am. Yeah, okay. Yeah, like it's natural number sets inside the real numbers. Okay, like I have a surprise for you. So first of all, can someone define what do we mean by cardinality of a set? Number of elements in the set. Okay, so what is the cardinality of the set of natural numbers? And what is the cardinality of the set of real numbers? So, like twice the infinity, not exactly, but let's see. Like, can you get a feel that the definition of cardinality we have right now is actually limited to finite sets? Like, we cannot use that definition to define the cardinality. Like, what numbers will you assign to n and r so that the number corresponding to r is greater, or something like that? But the strategy is that like we don't know how to assign numbers to the cardinality of natural numbers or the cardinality of real numbers. Fine, but we can have a strategy to compare them without assigning any number. So I would like you to take some time and read these 3 points, like, and try to understand what is going on. Okay, so to give you an to give you a picture of what is going on, the first statement says like if I have my x here and my y here, the first statement says that for every x I can find a unique y and assign x to that y. Like we can do this for all elements of x. You can like visualize this like the set x and y are having a war between them, where y is telling that no matter whichever soldier you send, I have a soldier which is ready to fight with you, and if you send the next soldier, I have a new soldier which is ready to fight with you. So does that make sense? Like, so what y is trying to tell to x is that my army is at least as big as yours. So is that fine? Now to give you a picture of the second statement, here we start with y and assign to it the elements of x. And what do we need to make sure that y, the cardinality of y is greater than that of x? Like we need to make sure that all the elements of x are covered by this assignment, right? You can visualize it that the elements of y are trying to make friends with the elements of x. In like one person here is going to talk to this person here, to a unique person, in such a way that at last no person in x feels lonely, right? And while we are making wars and friendships, the third statement should be clear, right? Like if a set sits inside the bigger set, its cardinality cannot be more than that of the bigger set, right? Is that clear? Now to give you a better grip on these 3 points, let's see what happens when we put one set to be n, or to be precise, when we put our y to be n. Now the first statement in the next slide is similar to the first statement here, which says that we can count the elements in x, like saying that the cardinality of x cannot exceed the cardinality of the natural numbers if we can count all the elements of x. So can you give like an example of a set like whose cardinalities cannot exceed the cardinality of natural numbers?
1, 2, 3, 4.
Okay, finite sets, right? Can the cardinality of the set of natural numbers exceed the cardinality of set of natural numbers? No, right? By the same, like we can count the natural numbers, although our counting will never stop, but we can still keep on counting, right? Now, similar to this second definition, an analog, like a very similar statement we have here, is that we can make a list of all the elements. And what we are doing while making a list, that for successively for natural numbers in order, I am assigning each element of x here. Like in the end, this will turn out to be my whole of x. So till now, any questions? Anyone? Okay. So now let's come to this result. And here I am saying that the set of cardinality of the set of integers cannot be more than the cardinality of the set of natural numbers, because we can list them. And kind of this was the surprise I was talking about. Can you understand the argument? you want to say something?
No, sir. I was asked. Like, I think it's similar to this, sir. Like, I was thinking that since we have infinite natural numbers, for each element in the real number list, I could map one natural number to each position by the way you asked us to compare the cardinalities of different sets. Then we would get that the cardinality of real numbers would be equal to the cardinality of natural numbers, because none of the means for each real number that's there, I can always find one natural number to assign.
Okay, I'll come to that. But for this time, let's relax and like appreciate the beauty of this statement that I have my set of integers here. The set of natural numbers sits inside it. It has some extra elements, but still, when put side by side, X has enough army to fight with the set of integers. And like this does not end here. I have more visual examples. You people understand Cartesian products, right? So here I say that the Cartesian product of n with the natural numbers is countable because we can count them as 1, 2, 3, 4, 5, 6, 7, 8 and so on. Like, and in a similar pattern we say that the Cartesian product of the integers by integers also we can count is like it cannot exceed the cardinality of natural numbers because we can count that also. Like I can count its elements like 1, 2, 3, 4, 5 and so on. In fact, like even the set of all rational numbers, it turns out its cardinality cannot exceed the cardinality of natural numbers. Like, can anyone guess how this can happen? Like, what are rational numbers? You can, yes?
Any number can be expressed in a ratio, but the denominator is low. So, for every, you can take a set denominator, and then for every possible numerator, you can assign a natural number.
Yeah, like the idea is like for every rational numbers, you can write it as p by q, right? Where p and q are integers, q cannot be 0. So, like, and every p by q you can map here in the set, right? Integers cross integers, and this set is not bigger than the natural numbers. So it turns out like such a dense set like rational numbers, which has a result corresponding to that between every two rational numbers there are infinitely many rational numbers. Such a dense set, its cardinality also doesn't exceed n. Now, like, let's go to the proof of the statement we were talking about, which was that the cardinality of the set of all real numbers is strictly greater than the cardinality of the set of all natural numbers. So, as I said, proof has the same flavor like the proof of there are infinitely many primes. So, like, it's a proof by contradictions. So, what should I assume first? Like the cardinality of natural numbers and the cardinality of real numbers are equal or less than, right? And what can I do in that case? What do you mean? Repeat.
If a subset of the real numbers itself has a greater cardinality than the set of natural numbers, then we can directly say even the cardinality of rational numbers should be greater than the set of real numbers should be greater than the cardinality of natural numbers.
Okay, like we are proving the complete opposite of that statement, right? Like I am trying to prove that in spite that rational numbers the cardinality of rational numbers cannot exceed, the cardinality of integers cannot exceed, but the cardinality of the set of all real numbers exceeds the cardinality of natural numbers. So I am trying to prove this by contradiction. So first, what will I assume?
That natural numbers is greater cardinality than real numbers.
Yeah, like the cardinality of the real numbers cannot exceed. And what can we do in that sense? Like we can count the real numbers, right? Or list the real numbers, as you can say. So here I have listed all my real numbers. Okay, no, actually not. Like my argument is that, like, forget about the set of all real numbers. The set of all real numbers between 0 and 1, even its cardinality is bigger than the set of all natural numbers. And to prove that, I prove it by contradiction. So let that the cardinality of all real numbers between 0 and 1, its cardinality cannot exceed the cardinality of natural numbers. So what can we do in that sense? Like we can make a list of all these proper fractions, right? Here I have 0.d11, d12, d13 and so on. And just to be clear that these are my digits, so they are always between 0 and 9, like natural numbers between 0 and 9. So suppose we have made a list of all the numbers between 0 and 1. Yes? Like that's how we are comparing the cardinalities. Like we have assumed that the cardinality of real numbers cannot exceed the cardinality of natural numbers. And what do we mean by that? We can list all, like based on our assumption, I am saying that statement. Yes, like I'm coming to that. So similar in nature to the primes, like I have assumed that they are like the set cannot exceed the cardinality of natural numbers, and I think I have collected all the real numbers between 0 and 1. Now like similar to the case of prime numbers, can we find a tricky number here in this case? The idea is to do that. Like what is your idea?
The first row we take a number that's not d1, you replace only d1, like if d1 is any number like 0, 1, 2, 3, 4, like if it's 2 for example, you take a number that's not 2 from the set of 0 to 10. Then in the second row you take the second element, it's d2, 2, and only that element you change, and you only change d3, 3 and d4, 4, so that it never match any of the number in your code.
Yeah, that's correct. Nice. Like that will be my idea. Like I want to come up with a tricky number, so like it will be like x1, x2, x3, x4 and so on. So what I do, I take my x1 something different than d11, I take my x2 something different from d22, I take my x3 something different from d33, and I do that. Like that's why the method used in this proof is actually called Cantus diagonalization method. Cantus because Cantor was the one who came up with this idea, and diagonalization because we are going along the diagonal. So like, and now how are we sure that we have not included this number in our list anywhere? We need, although it's like very clear to us by this point, but can we make some arguments regarding that? So moving on, like suppose I think I have listed it in some index of some natural number n. So how will the number at index n should look like. It's like 0 point d, n1, d, n2, d, n3 and so on, right? Does this make sense? And since our x1 is not equal to d11, x2 is not equal to d22, x3 is not equal to d33, in that pattern we can say that xn is not equal to dnn. Does that make sense? Right? So like for any index n, I can see that the numbers disagree at the nth decimal place. So actually it turns out that this element is not anywhere in my list. And it doesn't matter whichever list I take, I can use the same strategy to come up with a decimal proper fraction which does not lie in the list, right? So actually this contradicts that I can list all my real numbers, and actually that's kind of the end of my talk. In the end, I would like you to, as a take back from this talk, I would like you to think about these questions, like, can we have a set whose cardinality is greater than the cardinality of R? And by greater I mean strictly greater than the cardinality of R. And the second question is that, is there a set S which contains all the sets? Like no set will have more elements than that set. A pattern you can see that a pattern you can see, not a pattern, like an observation you can make, like if you can show that, if you can prove the second question, you have actually proved the first question, right? You have actually proved the first question. And the point, I would like to make one more observation. Yes? The second question is that...
Sir, one doubt.
Yes, I'll come.
Sir,
Yes?
sir, why can't we use that same method to prove that the set of all rational numbers is greater than that of natural numbers? Because we can also take infinite number of rational numbers between 0 and 1 and do the same way, right?
Okay. So for that, are you sure that you will change, you take for some point in decimal, you take a digit different from that digit, are you sure that you won't get an irrational number?
But we can get a rational number, it's a probability, right?
Probably, are you sure about that? Actually, we have a proof of why the set of rational numbers its cardinality cannot be greater. And here, we are not, I'm not convinced, because what if I take, from the first, at some nth element, I take my digit to be different from x and n. How am I sure that I'm not getting an irrational number? And
so we can say that it's a probability, right? We can say for sure cardinality of R is lesser than cardinality of n, cardinality of rational numbers.
Cardinality of?
Q, sir. Cardinality of Q is, we can't say for sure it's less, but we can say probably it's...
No, actually, I have a proof. We can prove that, the cardinality of the rational numbers cannot increase the cardinality of z cross z, right? Because every rational number I can write it as p comma q.
Yes, sir.
And the cardinality of z cross z, you can see that it does not extend beyond the cardinality of the natural numbers. Yeah, it's equal. Yeah, we can find that back. Right. So does that, like,
Okay, sir.
do you get some idea?
Yes, sir.
Yeah, actually, like these concepts, like there are a lot of we need to introduce a lot of technical terms to explain these concepts. But here I was just trying to give you an idea that these things can happen, like when we move from the finite case to the infinite case. So in the end, like I have some time, like, and the spirit, like another thing, like we were not like trying to take very fancy statements or making very fancy arguments. Like if our statements were simple, our arguments were simple. So in that spirit, I would recommend you to like look at the proof of like some statements which we probably like don't spend our time proving on it. Like the sum of all angles of a triangle is 180 degree. A number is divisible by 3 if and only if the sum of its digits are divisible by 3. Proving the Pythagoras theorem, or something like the permutation and combinations, like how does NPR come, how does NCR come, things like that. With that, I would like to end my talk. Any questions?
Sir, if we take natural numbers as a set and then take inverse of natural numbers as another part of rational number set, then we'll have numbers like 2 by 3 missing, no sir, from natural numbers, because 1 by 3 is already a set of 3, I mean matched with 3.
Okay.
So doesn't that mean that rational numbers are larger than natural numbers?
Like you came up with one strategy of mapping elements, right?
Yes, sir.
What if there exists another tricky mapping, like we don't know, like in some list we can, there's a possibility we can cover all the rational numbers, right?
Yes, sir.
So do you understand like what I'm trying to say? Any other questions? Yes?
To answer your first question regarding whether or not there is a set that has a strictly greater cardinality than that of the real number set, could we quote the complex number set? Because the complex number set also includes the real number set.
Actually, like it will take some time to like prove that the cardinality of like complex number, you can see it as R cross R, right? So like at this point of time I don't exactly know the proof, but R cross R, its cardinality is same as that of R. Any other questions? Sorry for such a short talk. I was expecting it to be bigger. Okay, that's all for me.
Thank you, Satya, for bringing such an exciting and surprising results, like when we go beyond finite to infinite. And you are not alone in being surprised with all these things. Actually, mathematics, the development of mathematics that went through several developments philosophically. So it's very surprising, like a number, like when we say a number which is, we can have a chalk here. Yeah, that's very, yeah, I found it. Yeah, it's like very surprising, like a number which is infinitely extended, like on both sides, and like a number like even the cardinality of 0, 1 and this entire line, they are same. So it's surprising. Like it's like we are talking about, as Satya was talking, like the cardinality of n and z. Their cardinalities are same, even if it seems twice as large as n is. Yeah, this is very surprising. And there is a reason actually behind that. I am just saying I might be repeating some of the points what Satya mean, but there is a reason why we should be allowed to get surprised. There are two things behind this thing I want to, before we conclude today's session, I want to bring two things. So there are two philosophical ideas. One is Hume's principle. Hume's principle says that two sets have the same size if there exists a one-to-one correspondence. There is a bijection between those two sets. And it seems reasonable that if two sets, the points on both sides are connected through a bijection, they would be of the same cardinality. And there is another principle that is called Euclid Principle. Euclid Principle says that a subset, cardinality of a subset cannot be larger than its parent set. So it means that this n is a subset of z. So through Euclid's principle, so part cannot be larger than whole. That is Euclid's part-whole axiom. This is called Euclid's part-whole axiom. And they contradict each other. And the mathematicians, they had to choose one of them. And Hume's principle was chosen. Traditionally, this was chosen and this was not chosen. So, and we are left with a lot of surprises like we had during Satya's discussion. So we are just measuring the size of two sets through bijections, not through this is shorter set and this is larger. Yeah, that is true. Even 0, 1 cross 0, 1, its cardinality is equal to r cross r, and its cardinality is 0, 1, cardinality of r. It's a very simple proof, like just through decimal expansion. It's very simple. It's an artistic proof. We don't have time here, but it's an excellent proof that we can be discussed through decimal expansion. Like I just leave you, like, because some of you asked, just write this thing in this form and choose, like, map it with A11, A13, A15 cross A12, 0 point. This is 0 point. 1, 4. It's just a hint. This is a bijection between r and r square. That's it. So yeah, this is one of the strangest thing that Satya has brought to us, and we are fortunate that we are being aware of this philosophical conflicting ideas. So that is what, like, this is a great thing. So through this note, I again thank Satya, and I would like to bring an end to today's session. So tomorrow we'll, like some of you were asking about the quiz thing, we'll give you details in the morning.